Hey everyone, this is me, Dr. GB. In lab on Monday, I said I would follow up with y'all once I made some headway, and true to my word, I'm making a video to walk y'all through it. Now, when we were in lab on Monday, we ran into a bit of a pinch when we were trying to calculate the value for C-cal. So there were the key capacity of the calorimeter. There's confusion over number one, why do we keep getting the wrong sign for the calorimeter? We keep getting a negative value and it should be positive. Also, why is my calorimeter value like 13,000? When Dr. GB happens to know offhand the C calorimeter, although there's variation, it should be in the hundreds rather than the thousands. And so I've been doing some thinking about it over the past couple of days, and I realized that where it came from, where this error came from, is that we were using the wrong value for the delta H of solution, or for the delta H, alrighty? So the way a calorimeter works is we are trying to measure the Q of a chemical reaction. And in this case, the chemical reaction is dissolving ammonium nitrate in water, okay? So it's the process up here of solid ammonium nitrate turning into NH4 plus, or ammonium and nitrate ions, and aqueous means they're dissolved in water. Now, but with that coffee cup calorimeter, we're not actually measuring the reaction itself. We are measuring, so if this is our system, we are measuring how water, the surroundings, reacts to the reaction. Alrighty, so if ammonium nitrate is increasing in enthalpy, it's going to pull it from the surroundings, which would lead to a decrease in temperature of the surroundings. So the Q of the reaction is going to be equal to the negative Q of the surroundings, alrighty. So we're going to see the opposite change, and we can actually take the surroundings and we can bust that up into two components, alrighty. So we can bust that up into the Q of the water, so the heat absorbed or released by the water, plus the heat absorbed or released by the calorimeter, right? So these are the two components, alrighty. So the heat absorbed or released by the water plus the component absorbed or released by the calorimeter, we put a minus sign in front of it to change the directionality, and that should be equal to the Q reaction. Alright, so what we're doing here is we know the Q reaction because we can look it up. We can calculate the Q H2O easily. But what we don't know is the C is the heat capacity constant of the calorimeter. And so we do know the change in temperature that the reaction undergoes because we assume the calorimeter undergoes the same temperature change as the water. And so we can solve for the C-cal, and we can use it as a constant in later calculations. Now, where things went awry is actually our calculations here were correct in class already. So this is another way of saying 0 is equal to Q reaction plus QH2O plus Q-cal. Where we went wrong is that we had the wrong sign for Q reaction. All right, because it turns out that the reaction that we were using as our reference was this one up here already. So when we went to the back of the book and we looked it up, we looked up the delta H of formation for ammonium nitrate from its constituent elements. So we were looking up the heat of formation of ammonium nitrate from nitrogen plus hydrogen plus oxygen. Now, when we take these together, you're breaking weak bonds and building strong bonds, so this is going to be a very large, very negative value. So a lot of heat is going to be released when we make this compound. If this doesn't make sense, it will in a couple weeks when we do thermochem in class, I promise. Now, but this isn't the reaction that's happening in our calorimeter. We're not making ammonium nitrate for nothing. We're taking ammonium nitrate and we're dissolving it. Alrighty, so it's actually the reaction that we're observing is actually this one. Alright, so the heat exchange that happens with this is our known value. And so if you go out to the literature or the internet and you look things up, the value for the delta H of solution is actually around 25,000 joules. Right now, you're going to need to go to the internet and look it up yourself, cite your own value. But I'm going to tell you it's around 25,000 joules, and we're going to simplify. So if we repeat our calculations using 25,000 joules, so the correct value as our delta H, it turns out the math is actually going to work out and be a lot closer to what we would expect. So because, again, we're positive instead of negative, and that makes sense. If our reaction is absorbing heat, it's going to take it away from the water, so the water temperature is going to decrease. So the sign change makes out with what we observe, whereas here, I kept looking at this negative value and being like, why do we have a negative delta H and our water temperature is decreasing? That doesn't make any sense. The other thing is we're also an order of magnitude lower, so our number is going to be smaller and more in line with what we would predict. So why don't you go ahead and repeat your calculations, but plug in a value of 25,000 for delta H instead. You can pause this. I'm going to write this out, and then I'll press play, and then my calculations will pop up on the screen. Alrighty, so I went ahead and I used that manipulation that we did in class where we solved for C-cal. So it's equal to minus Q reaction plus minus parenthesis Q reaction plus QH2O, or minus Q reaction minus QH2O divided by delta T. And so you see here, if we have a positive value for delta H reaction, and we have that negative temperature change, it cancels out to give us a positive value for a calorimeter constant. Now, even if these are your experimental values, your number is going to look a little bit different because you're going to look up a different value for delta H of solution. And you may see if you had a larger or a smaller temperature change in this, you'll see a different value in your calorimeter constant. Do not worry. As long as you have followed the same convention as I have, you're on the right track. Alrighty, so as you continue to progress, you're going to need to check your calculations for delta H reaction against the literature. So there's two ways you can go about this. Number one is you can use the delta H reaction. So you can just go ahead and you can, from Google, alrighty? So you can go to the internet and Google what is the delta H of solution for ammonium nitrate, and you get a value around 25 kilojoules per mole. Again, do not use this value from me. Go find it on your own. The second option is this is what Dr. GB started to try to show you to do, and then she failed because she had a brain fart because she had not written the class lecture on it yet. And that is, you can use the delta H reaction to calculate. You can use the delta H as a formation to calculate the delta H of reaction, but you can't just use it for one part. You have to use all the delta H of the reactions. And so the way it works is we can calculate the delta H for a chemical reaction by adding together the, so we put an N there for a number of moles actually. So together we can calculate, if we add together the delta H of formation for the products, so if we minus the delta H of formation of the reactants, that actually gives us the delta H for the reaction total. So what Dr. GB did in class is Dr. GB was like, oh, we just looked at the delta H of the reactants and said that was the reaction. So we only did half the math. So what we have to do if you want to use the values from the table is we take our reaction here. We start off with, not aqueous, we start off with solid ammonium nitrate, and it breaks up into NH4 plus and NO3 minus aqueous in solution. So to find the delta H for the reaction, we have to have the delta H of formation for NH4 plus the delta H of formation from NO3 minus, and subtract the delta H of formation for NH4 and NO3 minus. And so if we go into our appendix, and this is appendix H, all right, what we can do is we have our value for the delta H of formation for NH4 plus is negative 133.26 kilojoules per mole, plus the value for the enthalpy of formation for nitrate, which is minus 206.85 kilojoules per mole. And then finally, we subtract the enthalpy of formation for ammonium nitrate, which is a value we already found, which is negative 365.6 kilojoules per mole. And if we add all three of those values together, we get positive 25.75 kilojoules per mole. So as you go through and you do your other directions, you can go Google, what's the delta H of neutralization for NaOH and HCl? Or you can go and you can use the enthalpies of formation for the products and the reactions to solve this. Now, if you're like, Dr. GB, I need more help, I'm going to follow up, and you can go to the videos that I'm going to post for thermochemistry today. And one of the videos is called Calculating Enthalpy Changes 2 Ways. That will walk you through how to do this. So you're just a little bit ahead of the game.